Hello everyone, welcome to this lecture number 47 of the NPTEL course on Riemannian geometry. So last time we wrote down a formula for Jacobi fields that vanish at the initial point. So let me remind you of that. So if gamma is given by this radial geodesic, then any Jacobi field which vanishes at 0 and whose derivative, let us say at 0, is given by w, is given by this formula. So it is basically the derivative of the exponential map at the vector tv applied to the vector tw, right. So as a consequence of this, if you are using normal coordinates, let us say x1 up to xn, and suppose w is given by wi del I at p, then the Jacobi field is given precisely by just scaling the components wi, right. So a very nice consequence of this formula for the Jacobi field in normal coordinates was that we have a Taylor expansion for the metric components in of course normal coordinates. So Gij of x is given by the Euclidean part delta ij, then the first order terms vanish because we are using normal coordinates, so the linear terms vanish, the first derivatives of the metric components vanish. The quadratic terms are given precisely by these curvature terms, okay. Right, so today we are going to use this formula in this lecture to give geometric interpretations for the various curvature notions that we have introduced. So let us first start with sectional curvature. Okay, so here is the proposition. So let pi be a two plane in the tangent space at p, let up epsilon, which is the image under the exponential map of the ball of radius epsilon in the tangent space. So let this be a geodesic ball so that I can use normal coordinates on this. So let Cr tilde be the circle so let this be a circle of radius r with center at the origin in the tangent space, such that r is, let us say, smaller than this epsilon, and let Cr be the image under the exponential map of Cr tilde, okay. So you should think of this Cr, let me draw a picture quickly, okay. So this is 0p, so Cr is some circle here of radius r, so that should correspond to some circle. So this is your image under the exponential map Cr, and this is Cr tilde. So you should think of Cr as some sort of circle with center at p in M, okay. So let Lr be the length of Cr, okay. So then we have the following formula for the sectional curvature. So the sectional curvature of this plane pi p. So if you remember, we were also using this notation k of pi p. This is precisely given by the limit as r goes to 0 of so there is a factor which I shouldn't forget. So this is equal to 3 divided by pi of the limit as r goes to 0 of 2 pi r minus Lr divided by r cube. Okay, so let me, before proving this, let me make a remark. So in flat space in Rn Grn, clearly Lr is equal to 2 pi r, right. This is our favorite formula for the circumference of the circle in a plane, right, from high school. So what this tells you is that if the sectional curvature is positive, then this Lr is going to be less than 2 pi r for r small. Okay. So you in fact see this on a sphere, for instance. So so let us say we take the sphere and we look at, this is actually an explicit calculation that you can do. Let us say you have a circle at the azimuthal angle phi, right, and let us say it is a circle of right where this distance is r. Okay. So you basically go an r distance along a great circle and that traces out a circle. Then one can actually check that that this Lr will be 2 pi r times a factor where this factor is strictly less than 1. Okay. In fact, I think it's something like 1 minus cos phi or something like that, where phi is the azimuthal angle of that circle. Okay. So so this is an explicit calculation that you can do, and in fact as you see this will be strictly less than 2 pi r. Okay. So this sort of gives you the intuition that suppose you are on a positively curved space, then the geodesics sort of try to come together, so that if you go an r distance away and look at the corresponding circle, then that circle will tend to have smaller length because the geodesics are trying to come together. On the other hand, if you are working on a space with negative curvature, the geodesics will tend to move away, so that if you now go a distance r and look at the corresponding circle, that will tend to have a length which is larger. Okay. So that's the intuition. Okay. So let's prove this this proposition. So let E1 En be an orthonormal basis for the tangent space at P, and let x1 to xn be the corresponding normal coordinates. Okay. Also we choose this basis such that the two plane that we are looking at is precisely given by the span of the first two basis vectors. Okay. Okay, so then one can give a formula for the circle. Then the circle is basically just given by x1 is r cos t, x2 is r sin t, and all the other coordinates are 0, right, because this two plane is spanned by the first two basis vectors. Okay, so now let us just calculate the length of this curve. So to calculate the length, I have to calculate the speed squared, I mean I have to calculate the speed. So let us first calculate the speed squared. So that is Gij of Cr of t times xi dot xj dot. Okay. but clearly the only surviving terms are going to be when so this is non-zero only when ij are either 1 or 2, okay, because the circle for x3, x4 etc. they are all identically 0 on the circle, right. So this is basically just going to be G11 of CR of t times x1 dot squared plus 2 times G12 CR of t x1 dot x2 dot, okay, plus G22 of CR of t x2 dot squared. Okay, so I calculate. I use the Taylor expansion for the metric. So this is going to be so let's analyze each term. So what is G11 CR of t times x1 dot squared? Well, by the Taylor expansion this is given by delta 11 which is 1. So 1 minus 1/3 you will have curvature terms. Now curvature terms will be of two kinds. So you will firstly have G1 1 x1 squared minus 1/3 R1221 x2 squared minus 1/3 R 1121 x1 x2 and the corresponding R1211 x2 x1. Okay, this whole thing multiplied by x1 dot squared. Well, x1 is r cos t, so x1 dot squared will be basically r squared sin squared t. Okay. Now by the symmetries of the curvature tensor, this is so of course these are curvature tensors at P. So by the symmetries of the curvature tensor, this is 0, similarly this is 0 and this is 0. Okay, so the only surviving term will be, so this is 1 minus 1/3 R 1221 at P times x2 squared which is r squared sin squared t plus order of r cube. So there is a order of mod x cube here times r squared sin squared t. Okay, but then note that r of 1221 at P is precisely the sectional curvature of this plane. Okay, because del I at P del 1 del 2 at P, their norm squared is 1, right. So this is precisely the sectional curvature term. So this is precisely 1 minus the sectional curvature term by 3 times r squared sin squared t plus order of r cube times r squared sin squared t. Okay, so this is the first term. Similarly, you can calculate the second and the third term. So I won't bother you with the details. So similarly, let me just give you the formulae. So G12 of CR of t. So the second term is 2 times this times x1 dot x2 dot. This is given precisely by minus 2/3 of the sectional curvature term times r to the 4 sine squared t cos squared t. Okay. And similarly G22 is given by 1 minus 1/3 the sectional curvature term r squared cos squared t times plus of course O of r cube. So I should say that these are all with sort of correction terms given by higher order terms times r squared cos squared t. So now if you add up all of this, so adding up, you use your favorite trigonometric identity r squared plus sine squared t plus cos squared t is 1. So if you add up all of these, you get the following formula. So you get r squared minus the sectional curvature term by 3 r to the 4. In the bracket you will get sine 4t plus 2 sine square t cos square t plus cos to the 4t, and then the higher order term order r to the 5. So again the stuff in the bracket is just sine square t plus cos square t whole squared. So eventually you are just going to get this. Okay. So now I want to take the square root of this. So the speed of my circle is the square root of you can factor out an r. So it is a square root of 1 minus k of pi by 3 r squared plus order of r cube. So now I use the binomial expansion for square root. So note that the square root of 1 plus t is basically just 1 plus t by 2 plus something that is order t squared, okay, just by the binomial expansion for 1 plus square root of 1 plus t. Okay, so if I apply this to what I have in the bracket, so this implies that the length of this is going to be r times 1 minus r squared by 6 times this plus O of r cube. Okay. So now you plug that in and integrate. So the length of the circle is integral from 0 to 2 pi of the speed, which is just going to be 2 pi r minus pi r cube by 6. So you will have pi r cube by 3 times the sectional curvature term plus something that depends on a higher order term r to the 4. Okay. So from this now just solving for k of pi, and so k of pi is basically 2 pi r minus L r divided by r cube plus something that depends on r, and there is this factor of 3 by pi, right. So now just take the limit as r goes to 0 to okay, and we are done. So this gives us a very nice geometric interpretation of sectional curvature. We had two other curvature quantities, namely the sort of traces of the sectional curvature, namely the Ricci curvature and the scalar curvature. So let me also give you some geometric interpretation of the Ricci curvature. Okay, so remember, so recall that the Ricci curvature RKL was precisely RIKLI, right? So it was the trace of the components of the curvature tensor where you either sum over the first and the fourth or sum over the second and the third, right? So here's a proposition. Right, so also recall that the volume form, if you are working on an oriented manifold, the volume form is precisely given by the determinant of G times dx1 up to dxn, right, where G is the matrix formed by the components of the Riemannian metric. Okay. So then I have the following proposition. So if x1 up to xn are normal coordinates, then this factor that shows up in the volume element has a Taylor expansion which involves the Ricci curvature. So let us say this is centered at P. Okay. So how do you prove this? Well, we need the following elementary lemma from essentially matrix analysis. So let us say I take a n cross n matrix, okay, then I look at the determinant of a small perturbation of the identity matrix in the direction of A and take the derivative at t equals 0, then this is precisely given by the trace of A. Okay. So in particular, you have the following Taylor expansion. This is given by 1 plus the trace of A times t plus something that is order t squared. Okay. So why is this useful? Because your G in normal coordinates is a perturbation of the identity matrix, right? That is exactly the Taylor expansion for the components Gij, right. So in order to compute the determinant of G, that is essentially like a small perturbation of the determinant of the identity, right, or determinant of a small perturbation of the identity matrix. That is why this lemma is useful. So let us prove this lemma quickly. So let lambda 1, lambda n be eigenvalues of A over the complex numbers. So over C we know that every square matrix has n complex eigenvalues just by the fundamental theorem of algebra. So then we have the following formula for the determinant of I plus Ta is simply given by the product I from 1 to n of 1 plus t lambda I, right. So then if you want to differentiate, well, by the product rule this will be the summation over j going from 1 to n of lambda j. So you basically differentiate the jth factor multiplied by the product of all the other factors I not equal to j, right, and you plug in t equals 0. So at t equals 0, this will simply be the summation from j going from 1 to n of lambda j, which is precisely the trace of A. Okay, so that proves the formula for the derivative, and then the in particular part is just Taylor's theorem, right. Okay, so now I am going to use this to prove the proposition. So we know that Gij is delta Ij minus 1/3 R I KL J xi xk xl plus order of something x cube. So I just let A be the matrix whose ijth coefficient is given by minus 1/3 R ijk sorry I klj xk xl plus whatever is this sort of cubic term. Okay. Right, so maybe I should do this and let t be equal to mod x squared. Okay. So then my G is basically like a perturbation of A, right. So the determinant of G by our formula will basically be given by 1 plus mod x square times the trace of A plus something that is higher order, right. But what is trace of A? Well, trace of A is precisely given by minus 1/3 the Ricci curvature KL applied to xk xl divided by mod x squared plus something higher order. Okay. So this is going to be precisely minus 1/3 R KL, the mod x squared will cancel with the mod x squared xk xl plus something that is now cubic in mod x, because you have this this mod x term coming from the trace of A. Okay. So now again we take the square root of this by our formula, again that square root of 1 plus t is basically 1 plus half t plus higher order terms. So this half will multiply with the 1/3 and you will basically get 1 minus 1/6 RKL xk xl plus something that is higher order. Okay. So that proves the proposition. Okay, let me end the lecture by stating a corresponding proposition for the scalar curvature. So geometric Okay, so here's the proposition. that so the notation that we normally use is for any subset E of M, we write mod E is the volume of E, which is basically the integral of the volume form on this set E. Okay. So then the proposition is the following, that if you look at the geodesic ball of radius r and compute its volume for r small, this is going to have the following form. It is going to be omega n r to the n times some correction 1 minus the scalar curvature at p by 6 times n plus 2 r squared plus some higher order correction, okay, where omega n is the volume of the unit ball in Rn in the Euclidean space. Okay. So that means that the scalar curvature measures the discrepancy of the volume of this ball. So for instance, this implies that if you take a volume of the ball of radius r in Euclidean space, that is going to be omega n r to the n. So that is the leading term here, and the scalar curvature measures the discrepancy of the volume of this geodesic ball from the Euclidean corresponding Euclidean ball of radius r. Okay. So again let me I will keep the proof as an exercise. It is not an easy exercise, but I do not think I have the time to actually give the proof, but the idea is you have to use this formula for the expansion of the square root of determinant g and integrate. Okay. It's not a trivial exercise, but it's a really fun exercise to try to prove this proposition. Let me just end with a remark that if the scalar curvature is positive, then this implies that for r small enough, the volume of the ball of radius r is less than the corresponding volume in Euclidean space. Okay. And similarly, if the scalar curvature is negative, then the volume will be larger. Again, this sort of goes back to this intuition that if the scalar curvature, if the curvature is positive, then the geodesics sort of come together so that the ball that it will sweep out will in general be a smaller ball than in Euclidean space. Similarly, for negative curvature, the geodesics spread out, so the ball that it will sweep out will in general be a larger ball, right. Okay, so that's it for this lecture. Starting from the next lecture, I will use Jacobi fields to investigate this question on when a given geodesic is minimizing. Okay, so we'll the next few lectures will be occupied by this question. Alright, so thank you for your attention, and I will see you in the next lecture. Thank you.